Hi, I'm Bill Mather, and I'm just going to go over sort of the derivation of the non-inverting op-amp. Dr. Salmon did this in class, but I'm just going to go over it again. I'm not going to assume anything about the op-amp. I'm going to assume the op-amp just has a large gain A that's much greater than 1. And then I'm just going to try to derive the relationship between the V out with respect to V plus, which I'm going to assume is the input. I'm going to tie the op-amp in the non-inverting orientation, which is this. There's going to be a feedback impedance, which I'm going to call ZF, and then there's an impedance from the negative input to ground called ZI. And then I'm just going to go forward and derive all the relationships between the voltages, and then I'm going to get a relationship between V plus and V out, and that's going to end up being the canonical non-inverting op-amp relationship, which if you're an electrical engineer, you probably just know off the top of your head. So just to go through the steps, I'm going to just write down the equations of the relationships between the voltages. So the first relationship is I'm going to assume the op-amp has a gain of A, and I'm going to assume that gain A is much, much greater than 1. And we'll see where that comes in later. So that's going to be equation 1. V out is equal to A times V plus minus V minus. That's going to be equation 1. Now, for the second relationship, I'm going to just sum the currents into this node. So we know an op-amp has infinite input impedance, so there's no current going this direction. That I is infinite. So this current is going to be equal to this current. So IZF is going to be equal to IZI. So if I write down that relationship, this summing of currents into this node, 2 is going to be summing the currents into the V minus node. And that's going to be V minus over ZI is equal to the current from here, and the current from here is V out minus V minus over ZF. Again, it's just the voltage across this over the impedance and the voltage across this over the impedance of the two currents. And again, that simplifies into V minus is equal to ZI over ZI plus ZF times V out. Okay. So now we have these two relationships, one which is this V out is equal to A times V plus minus V minus, and the secondary relationship, which is the result of summing the currents into this node, which is V minus is equal to ZI over ZI plus ZF times V out. Okay. Now we're going to combine equations 1 and sort of this equation 2 to derive the relationship between V plus, which is our input node, and V out. Excuse me. So I'm going to combine 1 and 2 to give myself V out is equal to A, this large gain, times V plus, which is my input node, minus ZI over ZI plus ZF times V out. Great, now I have an equation for V plus and V out. So now I can simplify this and I can just eventually get V out over V plus, and that will give me the transfer function G, or the gain function G. So I'm going to move V out to this side, keep V plus on this side. That's going to give me V out plus ZI over ZI plus ZF A V out is equal to A V plus. Okay. Now here's where we can use our approximation. If we combine this term over here, we'll do that in the next step. So that gives us ZI V out plus ZF V out plus A ZI V out over ZI plus ZF is equal to AV plus. What we can do is we can see here if we divide both sides by A, This term and this term are going to be dwarfed by this term because a is very large. A is much larger than 1. So what's going to happen is this term is going to dominate these two terms because this is being multiplied by a very, very large number. Let's say 1e to the 6th, 1 million, and these aren't being multiplied by 1 million. So this term ends up being having a much greater effect. So we end up dropping these terms. They go to 0, or they get ignored because a is so large. If we divide both sides by a, so we're going to go through, we'll divide both sides by a, drop these two terms, and then we just get zi over zi plus zf v out is equal to v plus. Now we can simplify this. We move the v out and v plus to get g. So we move this to get g. G is equal to v plus over v out, over v plus. And v out over v plus is going to give me zi plus zf over zf, which simplifies into, this is zi, which simplifies into 1 plus zf over zi. So again, for the non-inverting op-amp, we just go through this entire process of relating the voltages at the output to the voltages in the input through the gain A, and then summing the currents into this node. And after we do that process, we just can go through the math, and eventually we get this relationship. G is equal to this term, 1 plus the feedback impedance over the input impedance at V minus. Okay. So again, if you had larger impedance terms here, like you do in the homework, you can just lump them all down into one impedance. So if this was a capacitor and a resistor and an inductor, you can just lump it all into one impedance. If this is a resistor in parallel with an inductor, again, their inverse is sum, but then again, you just get one impedance in the end, and you can go through this whole process to show this. Normally, with an inverting op-amp, what we can just say right off the beginning is we can say that the two inputs, as long as there's a negative feedback path, are the same voltage, because the op-amp is going to try as hard as possible to keep those two voltages equal. And if you just assume that V minus is equal to V plus, you can just use equation 2, and instead of having V plus here, you just plug in, instead of having V minus, you just plug in V plus, and again, you pop out the same answer immediately by assuming that these two voltages are the same thing. But you can see, even if we consider this gain much larger than A, we get the same thing. We just step through the math. A is much larger, these two terms fall away, and then we go through and we get G is equal to 1 plus CF over CI. Okay, hopefully that will help with homework. I'll see you guys at recitation.